Welcome to the Phase Space Invaders podcast. We're coming back after a break with Season 4. Two quick advertisements before we jump into the episode. Firstly, you can now support the podcast on buymeacoffee.com/phasespaceinvaders, all written as a single word. So I've been covering all the subscription fees for the editing and hosting tools out of my pocket, and I will continue doing so. But if you value what I'm doing here, I will very much appreciate even your smallest support. Secondly, with the help of Tamar Schlick, we got a commentary published in Biophysical Reviews about this very podcast. So in case you ever need a scholarly reference for the podcast itself, feel free to use it. But now to the episode number 25, where my today's guest is Ivet Bahar. Ivet is a director of the Laufer Center for Physical and Quantitative Biology at Stony Brook University or State University of New York. She's mostly renowned for the development of theory and applications of elastic network models in biophysical research across scales from individual proteins to entire chromosomes. With a foundation in this conceptual framework, she successfully explored research programs in evolutionary biology, allosteric and drug design, genetic pathology, and many more, recently earning a seat in the National Academy of Sciences of the US. So we start the conversation with a general overview of the elastic network theory and its applications to biology, as well as its strengths and limitations. Ivet then tells us about the specific takeaways from the different lines of her research, talking about evolutionary dynamics signatures, mode excitations in allosteric effects, as well as her recent research on the relevance of hinge regions for drug discovery. We talk about the relevance of the proteins as graphs picture for machine learning and end up with a few general reflections about the complementary roles of persistence and alertness in scientific careers. But then, enough of me talking. You should hear all that directly from my guest. Ready? So, Ivet Bahar, welcome to the podcast.
Thank you.
So, Ivet, you made innumerable contributions to the computational biophysics of proteins, coming from many different angles, from evolution to drug design to what can now be called dynamics. But most of them have a common denominator, and that's your, I dare to say, favorite computational tool, namely elastic network models. And I have to say, thinking about this simple concept really gives you access to such a broad and universal set of insights that in hindsight I can't really say I'm surprised by the impact your work has had on the field, but how did you decide to make it the cornerstone of your research toolkit in the first place?
That's true. The network models that we've been using have been very useful for a quite broad variety of applications. Usually, I'm more driven by specific biological questions. For example, when there were, let's say, high C data for determining the chromosomal organization contacts, gene-gene contacts, or contacts between gene loci, I immediately realized that, this is a field we could easily explore with our network models. And that's what we did. And that helped us gain new knowledge. So we were able to relate those contacts to gene-gene correlations, co-expression data. And to me, it was fascinating because, we've been always thinking of the DNA as an alphabet of 4 different types of letters. And now we are talking about a 3-dimensional structure that's also moving. And, it's totally physics-based after all, or mathematically driven our approach, and we are able to interpret lots of data based on this type of network models. So that was an example. But I think there are lots of different ways of also thinking. Another classical example I have been broadly using, is the allosteric communication. So when it comes to signaling, any signal actually, any type of conformational change that propagates, I think still network models are extremely useful. Obviously, the Kirchhoff matrix that we use, or adjacency matrix, they have been used in electric circuitry as well. So it is a natural tool, if you wish, to try to understand phenomena of biological interest. So first, I'm intrigued by a biological question, and then I try to see what would be the best tools to deal with it. And so elastic network models have been very useful. Of course, we do molecular simulations and machine learning models. And in recent years, we've shown that to combine them is even better.
Right. In the end, we all are sort of generalists with some minor specialization, right, in one subfield of the whole landscape of methods. But to go back to the basics, do you care to elaborate for our listeners, what is the most basic notion of the network model and how it applies to, let's say, protein structure on protein research broadly?
So the network models are a good representation of the geometry, actually, or the structure. So if you think about it, we are taking a complex system, and now we are representing it in terms of nodes and springs. So it is a huge simplification to represent a material or a biomolecule or a system of interactions by such a simple model. Now, the most commonly used network model, anisotropic network model, uses the alpha carbons of individual residues as the nodes, and then uses harmonic springs of uniform force constant for all amino acid pairs whose alpha carbons are within an interaction range, let's say 10 angstrom. And then we just use the PDB coordinates. We used to use PDB coordinates. Now we are also using AlphaFold database. We just use a known structural information on the residue coordinates to build the network model for the protein or the complex. It's equally applicable to proteins or DNA, use RNA, etc. So once you build this network, now you have a platform, if you wish, for doing lots of analyses. One of them is, as you know, the mode decomposition. We try to see this equilibrium structure, because by definition, what we're using is the equilibrium structure. Whether this equilibrium structure has certain modes of relaxation. And we hypothesize that those modes of relaxations are, the accessible movements, are what the structure actually uses in response to stress, in response to whatever necessary functional requirements are. So that's one thing, mode decomposition, understanding the spectrum of modes. The other type of analysis that we do is we try to analyze based on that, what are the critical sites, critical nodes of the network. And we try to see whether those critical nodes have been indeed observed to be evolutionarily conserved or have been targeted by drugs, etc. So the model is very simple. What is unique and what makes it work is that you have a unique analytical solution. It's not simulations. You have one unique analytical solution for every given structure, dependent on all the 3n coordinates, if you have n residues, let's say. So we are not considering local interactions, but we are considering the coupling of the entire network. And we're having a unique solution for the spectrum of motions. I think the mathematical rigor, mathematical precision of the theory is helping to kind of offset the physical approximations, because it is purely based on geometry. And if you would like to talk in terms of energetics, this is purely entropic. There is no specific interaction. Now, we know the limitations that in some cases, especially in drug discovery, it matters. The local interactions are important. So we complement it, we design hybrid models, we complement with other methodologies. But the essence of it, this framework or this graph theoretical approach is actually very powerful it just gives a good description of the anthropic effect.
Right. So you never bump into computational resource problems with this method, at least. But
absolutely true. We have, we don't run into computational resource problems. The only thing is the size. Sometimes we like it to apply to even larger systems because the approximation of this type of harmonic potentials or Gaussian distribution of interresidue distances, it is strictly true in the limit of an infinitely large network. And when it comes to smaller systems, now specificities, unharmonicities, all those things matter. But when it comes to the global dynamics, which is the collective motion of the entire big network for systems that are not typically resolved by cryo-EM, I think that is where those network models are most useful. And we have been developing, we're now using directly electron density maps to build the network models. We can apply it to many hierarchical levels, different levels of resolution. What is beautiful to me is the fact that the most cooperative, lowest frequency, or what we call the softest modes of motions, are very robust. They are maintained across several different levels of representation. So that's the essence.
Right. And while we are at it, well, there are certainly patterns that you can find if you look across the proteome, right, or across evolutionary timescales. What kinds of patterns have you been able to pinpoint in proteins looking at exactly this kind of conserved modes or these robust modes that are preserved across, say, classes of proteins?
Yeah, that is, in biology, bioinformatics actually started with analyzing sequences, right? Sequence motifs, or there are signature sequences that are known to perform certain functions. And then there are signature structural motifs that would be accomplishing a certain function. And they have been recruited by nature in many different proteins, not only one. Now, then we recently came up with this concept of signature dynamics, which means there are certain movements. Let's say in the simplest case, if it's a two-domain enzyme, there's a cleft in between and there's this opening, closing. This type of movement is so useful for, enabling the binding of a substrate or then surrounding the substrate. And nature has been using the same mechanism of motion, some torsion, some bending, etc., in many different proteins. Now, it is possible to understand what is the repertoire of all motions that are accessible. And then we went a little bit further. We went deeper a bit. We considered families of proteins that share the same structure. Of course, in our model, structure dictates the network model, which in turn determines the dynamics, which relates to function. That's the way everything connects. Then when we analyzed families of proteins, we could see that many of them share the same global dynamics. So this is like the signature dynamics of this family, which makes them perhaps members of the same family. But then we can see subgroups that have their own specific variations in their dynamics. And then that's how the function has been specialized, if you wish, to accomplish different requirements. So it is possible to approach the universe of proteins or protein families from this dynamic perspective to understand, their mechanism of function, how this type of function has been differentiated or became more specialized. And that brought us to many, many evolutionary arguments. So it is not only the sequence or structure, but the dynamics that needs to be conserved in the first place. But now you can have many variations to increase specificity.
All right, so it makes you think of this kind of convergent evolution, right? That evolution comes up with the same, through different means, comes up with the same solution to several different problems.
Absolutely. You're absolutely right. So there's some kind of convergence. many systems chose, even though their function might be different, they chose the same mechanism. And however, there's also divergent evolution, because from that point, if you would like something to be more specific to a certain environment or species, there is also divergence. Yeah.
Right, you can evolve allosteric pathways or modes as you probably prefer to think about them, right? I mean, you mentioned this two ways of thinking about allostery.
Yeah, that's an interesting topic. Allostery, there are so many definitions in the literature, and what my understanding is that it's a cooperative response to some kind of perturbation at a given location of the molecule, which is not necessarily the active site, but then affects the activity. And mostly it affects the interaction with other proteins. So that is my broad view of allostery. And these cooperative events are actually things that we can predict by network models, elastic network models. Now, there have been another group of studies, and we have even, our group has been publishing like that, trying to see the network as a platform where you have a framework, let's say, where you have propagation of signals through Markovian dynamics. So
more like time dynamics, time series.
You can define transition, matrices or transition rates to go from one node to another, first passage times, etc. And you try to understand when you perturb a given region, which you call the sensor, how is this signal propagated through what we call effectors. So we try to dissect the structure in terms of sensors, effectors, what are the spots where you can, alter the dynamics significantly, etc. So that has been this type of approach based on connectivity, essentially, and some kind of propagation of signals has been also broadly used for understanding allosteric responses. My preference is the first, where we have some intrinsic cooperative movements already. And when you change the cooperative it is not because there is a progression from one point to another, but things are moving together. And when things are moving together, if you really affect one end of the structure, now that particular movement, especially if you perturb the hinge site, that movement will be, collectively affected and impaired or, accelerated. To me, that's the way allosteric mechanisms. This is more an all or none approach that Monod, Women, and Changeux introduced, rather than a sequential event. Now, of course, this is a long discussion, and we've seen in many applications, in simple systems, early organisms, let's say, this all or none mechanism really works well. As the organisms get more complicated, we approach humans. Now, everything gets more sophisticated because we compared the chaperonin for bacteria, Groiagraes, versus those for mammalians that were more recently resolved. And we can see that in the case of Groial, yes, an all or none mechanism works. But when you go to higher organisms, to mammalians, now you have a combination of sequential and all or none mechanisms. It is more complicated. So we need all those theories actually to perhaps make better sense of observations.
Right. It's a common pattern that when we try to figure something out for humans, it becomes intractable.
It gets complicated. Complicated, but we learn a lot for simpler organisms, which form a basis. But we need to biology, unfortunately, in contrast to physics, biology has lots of exceptions or peculiarities. But still, the basic rules of physics, they help us a lot.
That's true. I often thought about all those, for example, old kinetic models that were essentially based on excitations of molecular normal mode frequencies and so on. And very often it was so hard to apply this to a biological problem, like to see how this excitation exists in an enzyme environment rather than in a diatomic molecule, right? Or something like this. But It's actually a quite useful concept once it's applicable. I agree. But you mentioned hinges, and I remember you recently went into exploring the hinge motion as related to drug design.
That's right. This is something, we've been always saying hinges are very important. And, many groups also have demonstrated, developed interfaces, etc., to identify hinges. Intuitively, we say, okay, since hinges play such an important mechanical role, hinge sites, if you target those sites, they ought to have some kind of effect on the function of the protein. So we have been always assuming that, but there was no rigorous, systematic examination of all existing, drugs, where they bind. Do they really bind any of them? Do they bind hinge sites, etc.? So since we always make this assumption, I thought maybe it is worth exploring rigorously now that we have access to tons of data. So we looked at FDA-approved drugs, their interactions with their target proteins, and tried to understand whether hinges have been indeed targeted by those drugs that turn out to be approved. Now, we know that most of the drugs have been, the structures that have been resolved show the binding at the active site, like the catalytic site of enzymes, which we call also the orthosteric site. Then more recently, we know that in some cases, you have drug resistance mutations, etc. Allosteric sites have been targeted. This a typical example is the ABL kinase. There are now new allosteric drugs that target this myristoylation site, if you are familiar with. Mm-hmm. And now there are even drug resistance mutations that arise there. Now, I thought the first one is more like a chemically important site. It's where the chemistry takes place, the orthosteric. And the allosteric sites are physically important. They modulate the interactions. Then I was thinking hinges could be also important as mechanically important sites. After all, we have papers saying enzymes are mechanochemical entities. There's the mechanics and there's the chemistry, and they are together. And mechanically important sites would be hinges. And it is very interesting. In this paper that now we published a few months ago in PNAS with a PhD student of mine, we showed that actually many drugs, existing drugs, do target allosteric hinge sites. And in many cases, what happens also is that hinge sites and orthosteric sites, they may overlap, they may be co-localized. So at least 40% of the drugs, the probability of targeting hinge sites is way above random probability. This has not been a strategy that has been, explicitly used in drug design, but it has apparently worked without planning to do that. So what we are proposing is from now on, why don't we just plan this way and try to target really the hinge sites, which we're already doing that in many applications.
Right. I guess historically, a lot of drugs that were supposed to be rationally designed eventually bound to places that just happen to be good at binding sites, right? So we don't always know where all the drugs were supposed to be binding. That's a fair point.
Absolutely. So everything started, as trial and error, and we still, we are very glad when we have anything rationally designed that works. But I think gradually with explosion of AI now, data, accessibility of data, we're going to see increasingly more rational design.
Well, that's the promise of it all.
Drugs is an example, Again, many repurposable drugs have been just discovered by coincidence. But now we have really powerful tools to understand what are the side effects, which particular drugs actually target those off-target proteins. And
Also for like technical reference, how do you define hinges in proteins? Because that might be not that obvious for someone who doesn't see a protein as a bunch of, blobs that move in a hinge-like manner.
Conceptually, the simplest thing is you have two domains connected, and there is a region that allows for the relative movement of the two domains. So this is like the intersection between two structural regions that undergo opposite motion. So one is moving like that, the other is moving, and the hinge is in between.
So it's very easy to detect in a network model, right?
Now, well, if we look at the structure, we can say, oh, this is likely to be a hinge allowing for that particular subdomain to swing. But you can do also mathematically, if you plot the movement along principal axis, along mode axis, there are regions that undergo positive movements and others that undergo negative. And then there is a crossover region. Mm-hmm. It is very interesting. If you look at the crossover regions, even though they may be sequentially separate, on the structure, they all co-localize in the same hinge that governs that particular motion.
Right. That looks like a good hint. And then that also helps you, I assume, understand the action of a given drug, right? Because not all drugs have the same biological effects. Some are activators, some are inhibitors.
That's right. And it's not only drugs, it is also mutations. For example, we have been now using dynamics information for determining whether a given mutation is neutral or pathogenic. So most of the mutations would be neutral, but there are certain, especially, of course, as sequentially evolutionarily conserved sites or very tightly packed regions in the structure, but also regions that play an important dynamic role. So we have been able to use this type of information on the motions, mechanisms of motion, and even the type of allosteric communication sensors, effectors that I just mentioned. If a given residue plays an important role as an effector of allosteric signals, its perturbation might be damaging. So we have many, many features that add up, in an algorithm, machine learning algorithm. Each feature is assigned a weight, learning from existing data. And now we're able to make very accurate predictions, depending on the data set, but it is certainly in the 90% accuracy levels for the consequence of point mutations. Now we're trying to extend these things to double mutants or insertions, deletions. These are less explored. But the same arguments that hold for identifying critical sites also hold for identifying sites that can't tolerate mutations. And you might ask now, if you use just elastic network model, you identify a site, but you don't know the consequence of a specific substitution. And that's true, we don't. That's why, we're using the network models in combination with sequence analyses as well as structural, analysis. So it is part of the information, but it is nicely complementing others, something that has been not enough explored.
I see. Yes, we have very good or increasingly improving tools for studying point mutations, missense mutations, but as you pointed out, there is no easy way to see the impact of, say, insertions, deletions in something like alchemical simulations, right? So I assume this might be a really, really interesting research to study.
Yeah, this is less studied. Of course, the other thing that we can't do, talking about what we can do, network models are, by definition, elasticity is a solid-like property, right? So they apply to solid materials. And proteins, to the extent that they are solid-like, we can apply elastic network models. On the other hand, there's a huge literature about IDPs, intrinsically disordered proteins. We can't use elastic network models for understanding the behavior of IDPs or IDP segments in general. And also, for example, when there is a new protein and we look at the AlphaFold database, there are certain regions that are structured, but others that are completely disordered, And these are regions where we can't apply our tools. And that's where we start also to use other, classical molecular simulations or some polymer theories also work for this type of disordered regions.
I see. I have a guest scheduled for this season who is an expert in IDP, so we'll talk about it more. I don't want to give it away yet, but there will be an entire episode dedicated to that. Yeah. So here we are in the folded regime. Still. Yeah, but it's interesting that this question of proteins viewed as graphs nicely extends to the recent graph neural networks and machine learning approaches, right? So you're at this interesting interface that has a lot of opportunities, a lot of insights that also have a nice future outlook.
The reason for that, Miloš, is that they are very efficient. You can serially apply the methodology to thousands of proteins and extract vast amounts of data. So you can't do on, very collective events, etc. So that the efficiency, the ability to generate, outputs very efficiently makes it possible to plug these tools as modules in other machine learning software.
And so I assume there are also many cases where this protein mechanics is actually important for protein function, not just as an enzyme or as allosteric communication, but in real biomechanics, right? So what about systems where the actual mechanics is part of the function?
That's right. Of course, we have mechanosensitive channels. The name already tells it all. And actin, tubulin, these are systems where the mechanics really matters. So that others have been, generating lots of interesting results on mechanically important systems. Yeah. I've been more focusing on membrane proteins a little bit, because membrane proteins are good targets for drug discovery, obviously. Mm-hmm. And like everyone else, we like big machines also, multimeric, multi-protein systems. But yes, there are tons of different.
What are the largest systems you have applied these methods to?
We apply to the nucleosomal pores, nucleosome. We apply to viruses, big viruses. And it's not only the capsid, but also the interior, the RNA or DNA, depending on the virus. So, there are lots of big supramolecular machines like the ribosome. So we have been quite a broad variety. We are testing the limits or trying to understand to what extent our theory and methods can explain observations or generate new information.
Right. In case of viruses, I imagine these are disassembly processes, right? Where the most sensitive part is, and which mutations actually, I imagine, correlate with that.
Yes.
I see. I asked you about what you think are important features in a scientist, and you mentioned persistence as one of the main topics. And I can see how exactly persisting in one fruitful approach can yield a lot of interesting results over the years. Yeah. So
there's also, what is also important is to be a little bit, some kind of awareness, to be alert. Because we have been benefiting from advances in experimental technology. Now there is cryo-EM, we have big structures. Or as I mentioned, there's high-C technology. Now we're machine learning, artificial intelligence. This is another technology we're using. So it is important to be persistent in general. But also one other thing I would mention is to be alert, just have a good understanding of, what are the new opportunities, the new areas we could further expand. And not to be shy, not to be reluctant to, move from one topic to another. Because after all, this is like exploration that we do all the time. And it gets more exciting when we explore new areas. So that's what I usually tell my students. Your PhD thesis or your master's thesis is not going to be, the topic that's going to define your career. But you will be exposed to new problems, and you will need to come up with new solutions. And when you have a very solid foundation in the first place, and secondly, the persistence and the strong desire to pursue, to dig deeper, there is no way you are not going to succeed. So you will succeed for sure. That is one thing I try to emphasize. The fact that, the important topics are changing all the time. And this is a really exciting time. And we just need to be able to use our knowledge, our tools to address new questions.
Right, there's this comfort that comes with staying within your favorite field. But as you say, the most interesting things come out of really, really jumping onto the new thing of the era, right? That can be a different topic every half a decade. I wouldn't say every year, maybe, because that's probably too flexible.
That's right. The other thing I also sometimes try to say is, in our field at least, we need a lot of patience. It takes sometimes a long time to find something of interest or to solve a problem that's really difficult, but it pays off. So it is worth pursuing, being persistent again and patient.
Well, at least if you use network models, you don't need to be patient running the simulations. But if you run atomistic simulations, you need even more.
That's true. For the network model, you don't need to be patient, but there are some tedious problems that require, to solve it, to come up with a good solution. Now we're trying to understand, for example, the connectome. How does the brain work? It is tedious. It is more complicated. Just a simple description based on the location of brain regions using network models is not sufficient. So there is this important issue of memory. For example, if you think of a Markovian propagation of signals, it doesn't work because Markovian processes just know the instantaneous state, right? Brain, we know that brain has memory, and the way it is being processed is much more complex than a simple linear process. So it is, then this requires some new formulation, adaptation to the specific system. At first, to see that our simple models don't work, it is kind of, let's say, frustrating at first. But then when you start to dig deeper, you try to understand what's needed, etc. So the persistence is very important.
Absolutely. I think what comes out of the research in artificial intelligence is that graphs or those networks have information embedded in them in a very non-trivial way, right? Like ChatGPT actually remembers things just through connections.
That's
now,
right.
Can you generalize that to biological networks? Do they remember things in this way of, encoding evolutionary information in a way that we cannot really access? And maybe there's a code to access this information. I think that's part of that is what you have been doing for many years, but perhaps there are new ways of approaching this question.
So it has been a pleasure to talk.
Okay. So Ivet Bahar, thank you so much
you're welcome. Thank you
for your
so
knowledge,
much.
for sharing with us what you have learned and explored.
It's very useful to have a dialogue. It's part of what we're doing.
I hope so. I hope people get inspired of your research and look into that and find applications to their own interesting questions, and that becomes a fruitful exchange in the long run. Thank you again for coming here and talking to me.
Thank you. Have a nice day.
Have a great day. Thank you for listening. See you in the next episode of Space Invaders.